There we go. So we are now in business. So the outline of my talk, I'm going to start with a brief introduction on both the lithium-ion batteries and soft X-ray XAS and the RIXS. And then I will go to my break session number 1 for questions. And in the second part of my talk, I'm going to share a few examples that we use our techniques and devices to study the cation redox, mainly transition metal redox in batteries. And then in the third part of my talk, we will switch gears to anions, which is mainly oxygen redox, but I will also cover some sulfur and fluoride if time permits. Okay, batteries, yes. Energy storage is now a very hot topic, and it's been super important in all ways, and we have it in our everyday life, from as small as these handheld devices in our pockets and the electric vehicles, which I call the intermediate size, and the big size, which is the power grids. And notice the energy storage is a key component in smart grids. And if we are talking about renewable energies like solar or wind energy, they have to be coupled with the energy storage thing. And the lithium-ion battery is so important that it's been awarded with the Nobel Prize in 2019. But although the Nobel Prize is awarded, that doesn't mean it's the end of the research. Actually, there are still tons of things to do. So first, I believe, yeah, these things all sound sexy, but real life is usually not as sexy as we expect. I bet you see these things over and over again when you ran out of batteries for your cell phones and you have to recharge it. And this will occur like more and more frequently because of a battery failure. And eventually at some point you have to replace your cell phone. I mean, I'm okay to replace my cell phone every 2 years, but if I'm buying a fancy electric vehicle, I just wish it will last a little bit longer. So we want our batteries to have long lifetime, and for electric vehicles, none of us want to see it catch on fire. So safety is always the most important thing. And for the power grids, because money is a big issue, and so everything we build in, we want it to be cheap. So there's a long way to go. And for those who are not familiar with lithium-ion batteries, so this is a demonstration of what you actually have in your lithium-ion battery. It comes into 3 parts. You have the cathode side, the anode side, and you have some electrolytes. So the cathode side, traditional cathode sides are transition metal oxide. So the first commercial lithium-ion battery is lithium cobalt oxide. And then on the anode side, the current commercial anode is the graphite, and people are trying to mix more silicon into it to improve the performance. And the lithium ion is a charge carrier. So when you have an open circuit, you have the electrons migrating along the electric wire, so you can have current. And inside your battery, you have your lithium ion migrating in order to balance the charge. So lithium ion really determines the upper limit of the capacity of your battery. And so when you have this charge and the discharge process, there's always redox reaction happens. So transition metal is a great material to undergo redox because they can access different redox state. And oxygen anions used to be treated only as a counter ion to balance the charge, was also interested to be found to be redox active. And many years ago, oxygen redox was believed to be a bad thing because you may end up with dioxygen gas. And you can imagine formation of gas in your cell can be potentially dangerous. And also, if you form dioxygen gas, it will leave the system and your reaction will not be reversible, which will kill your battery eventually. The recent studies show that the oxygen redox can actually be a good thing if you can have it under control, if you can keep it as, say, a peroxide inside your battery instead of forming oxygen gas, then it's going to greatly increase the capacity of your battery. Considering the atomic mass of oxygen versus the transition metals, if you can have your oxygen redox well under control, you can easily double or even triple the capacity of your battery. So people consider that as the next generation battery. And so right now we have a lot of issues with the existing lithium cobalt oxide. So it's the cathode side is right now the bottleneck, if you agree with me. So number one thing is it has a layered structure. It comes with a transition metal oxide layer, a lithium layer, a transition metal oxide layer, a lithium layer, and so on. And imagine when you just pump away the lithium ions, the structure tends to collapse or undergo some rearrangement. So we see these logos very often when you charge or discharge your battery. And people love to make analogies of like a water bottle for your battery. So when you charge it, you pour in water, and when you discharge it, you drain it. But it's actually not the case if you let me make the analogy. So when you when you discharge it, you have all the lithium ions migrate in, and it's a full bottle. But when you charge it, you drain all the water or you drain all the lithium ions, the structure tends to collapse, and the water bottle is going to become something like this. And imagine you have to refill this water bottle and see how many cycles you can end up with. So there are really a lot of things we need to improve in terms of the structural stability. And of course, as we mentioned, the safety is a big issue, and lithium cobalt oxide is highly flammable. And not to mention, we have to worry about the cobalt abundance in nature and the cost. So with the development of lithium cobalt oxide or the lithium battery field, the cost of the cobalt is going up dramatically. And there are also some discussions or debates about the aesthetics and the political issues about the source of cobalt, which has to do with some children labors or in cobalt mining in African countries. So we have a lot of driving force to go cobalt free. So this is where we are. So the first thing people would think is to replace cobalt with something in the same as a 3D transition metal. So with either manganese or nickel. So a lithium manganese oxide is a good option. Plus, cobalt prefers the layered structure, while the lithium manganese oxide can have a disordered Rocksalt structure, which is believed to be more rigid or more stable than the layered structure. And as I mentioned, the lithium ion determines the upper limit of your cathode. So if we can undergo lithium rich, means if we can mix in more lithium ion, we can potentially increase the capacity. In order to increase the lithium content, we have to decrease the transition metal content, which will lead to a lower capacity. But as I mentioned, it doesn't matter because we can try to activate the oxygen redox, which is 2. Then we can compensate that effect. And then experiments show that high valent 4D or 5D metal ions like niobium or molybdenum can be used to balance the charge and can make the structure more stable. So we can try to mix in more niobium or molybdenum. And interestingly, studies found that if we introduce more fluoride, we can increase the performance of our batteries. So here we see that when we have 0 fluoride and when we mix more fluoride, we can compress the release of the oxygen gas. And with fluoride, we can also increase the capacity and maintain the cyclability. So the full mechanisms of the fluoride is still not fully understood. We call the magic fluoride effect. but we know we should try to mix at least some fluoride in order to improve the performance. So this is how we start with our traditional lithium cobalt oxide to a somewhat complicated material like this. And this is what I call a rational design. But material scientists are not always necessarily rational. And sometimes discovering new materials is like cooking. So you're trying to have a mix of everything. And hopefully you end up with something good. And when I say good here, I mean a high dimensional metric. So here in this literature, it considered good to be a long lifespan, some great performance, nice safety, more high power and high energy density. And of course, you have to take cost into consideration. So you can see it's really hard to satisfy every criteria. And so people start from some simple component like lithium cobalt oxide and the lithium manganese oxide, and then they start to move to this NMC, which is nickel, manganese, cobalt, and NCA, which is nickel, cobalt, aluminum. And what's more, for the same component like NMC, you can have the 111 or the 811, which means you can have 33% of each, or you can have 80% nickel and 10% of manganese and cobalt. And every time you change the ratio, it will also change the performance. So it's really exploration in high dimensional space. And not to mention, we just published this paper with our with the synthesis scheme. So they call this a high entropy cathode material, which means they mix a lot of transition metals in it. And in this KM6, you basically have 6 types of cations, and they are trying to expand it to more cations. So it's really like a mixture of everything. And if you're lucky enough, you end up with something with great performance. Notice I was only talking about the successful stories here, but behind behind these successful stories, there are more failures we encountered. So unfortunately, there's no such thing as a journal of failure experiments. But as scientists, we are very interested in understanding success. And we're also equally interested in understanding why something doesn't work. So that's why we need a tool of choice. So here we use the X-ray spectroscopy. The reason X-ray spectroscopy is nice is number one, or the most importantly, it's element specific, which allows us to track the behavior of each individual element independently, one at a time, while you have a mixture of soup. So in the beamline I'm working at, beamline 8.0.1 at the ARS, it's a soft X-ray beamline, covers from about 100 EV to 1000 EV. So this energy range covers all the 3D transition metals and the common anions like carbon, nitrogen, oxygen, and fluorine. And if you want to make your system fancy, you want to mix in some silicon or sulfide, sure, we can deal with that. And for the heavy elements, we can also try to shoot for the M edge or the N edge. And another advantage is we don't have a strict requirement on the samples. So once you disassemble your cell, we can easily just load them and measure them. And notice when I say X-ray spectroscopy, I really mean a series of techniques. So a standard X-ray absorption is you're measuring the outcoming photon versus the incoming photon at a given energy. But this is not realistic for soft X-rays because your samples will not be transparent to soft X-ray. So instead, we can measure the total fluorescence yield. So we can measure the fluorescence we can put our detector at 90 degrees to collect the coming out of fluorescence photons, assuming the amount of fluorescence is proportional to the amount of absorption. And we can also measure the total electron yield. We can measure the compensation current. So I really like this figure, which talks about the penetration depths of a different method. So the TEY, the total electron yield, has a penetration depth about or probe depth of about 5 nanometers, which is a pure like a surface sensitive technique. While the hard X-ray is we don't worry about that here because we are a soft X-ray beamline. So the normal soft X-ray, the fluorescence yield, the penetration depth is about 100 nanometers. So we can call it subsurface or subbulk, depends on who you are talking to. And this penetration depth is enough for our for the particles in these battery materials. And what is more, we can try to isolate the coming out of fluorescence by their photon energies. So we can add a gratings here at our beamline. So we can, in this case, and then we can collect it using a CCD detector. So in this case, we will then end up with a 2D spectral. We can have the absorption energy in one dimension and the excitation energy on the another dimension. So we really end up with a 2D RIXS map, which really brings us an additional dimension, which makes it way better than the traditional 1D X-ray absorption spectra. So yeah, so what's more, the X-ray absorption is sensitive to the redox state. As I mentioned, it is very important in batteries. And the soft X-ray is sensitive to electronic structures, which is highly correlated with the reactivities. And even though soft X-rays is not good at obtaining geometric structures, I will share like one example that we can still obtain some information about the geometry indirectly. And of course, as I mentioned, we can track both bulk and the surface using the fluorescence method versus the electron yield. And with all that, I'm going to enter my first break, and I'll see if you guys have any questions or comments.
Okay, great. Thank you very much. That was a great introduction. I see 1 or 2 questions, but if anybody else has questions, please type them in now. Yulia, would you like to ask your question?
Yeah, it's mostly like a curiosity question. So in those commercial devices, what are the thicknesses of anode and cathode?
What is the what? Excuse me?
What are the thicknesses of cathode and anode?
Oh, the thickness is actually pretty thick. Actually, they're coming to multi-layers. But the good part is they actually, even though it's pretty thick, but they actually coming as small particles. They actually paste the small particles together. So that's why I'm saying the penetration depth of a few hundred nanometers is sufficient to be used to understand the behavior in the bulk.
No, I'm not asking about the penetration, that's what I understand. I just want to get a sense. Is it micrometers, millimeters? Just want to have a sense of the scale for real device.
Oh, real device. It's just the battery, the commercialized devices is actually about the thickness of your cell phone. But it comes into multi-layers. If you you can Google or YouTube like how to disassemble a lithium-ion battery, you can actually unwrap that and it comes into a long strip. And I would say a few hundred microns.
Okay, thank you.
You're welcome.
So I don't see any other questions, but I have one. In these transition metal oxides where you are jamming or overloading them with lithium, when you get to lithium 1.2 and then a mixture of transition metals, how much of that lithium is actually active, and can move out and participate in the charging?
It depends on your system. Actually, for the lithium cobalt oxide, we know only half of the lithium can be pumped out in theory. And so that's why we are trying to mix as much lithium as possible usually.
Right. Okay, thanks. So I don't see any more questions right now, but if someone has a question over on this part or the next part, please type it into the chat, and why don't you continue on to part 2? Yeah.
Okay, so part 2, I'm going to talk about some cation redox monitoring. So first, this is the electrochemical profile we have, or it's actually measured by our collaborators or the sample providers. So the x-axis is the capacity, or you can think of as the amount of lithium that's been pumping in and out. So the red would be the first cycle of charge. Oh yeah, the y-axis is the voltage. And the first cycle discharge, and you cycle it again in the second cycle, charge it in the second cycle, and discharge in the second cycle, and so on and so forth. And we are particularly interested when there's a dramatic change on the slope, because that usually indicates a phase change. So we can take the derivatives and find these key points for the samples. And we can just take them, isolate them, and measure them, etc. etc. Traditionally, people use the hard X-ray, and here let's take the manganese K as an example. So we have the reference for manganese 2+, manganese 3+, and manganese 4+. And this is good enough for us to see. We start with something in the manganese 3+, we oxidize it a bit, and when we charge it to high voltage, it becomes a manganese 4+, and then it goes back. But this is only qualitatively good, because we only know it's like the starting point, the end point, and something in between. It's really hard to tell whether it's like valence is 3.2 or 3.5. So that is the advantage of the soft X-ray. And if you look at the reference spectra of the manganese LH, the manganese 2+, 3+, and 4+ are totally different. Right? And we can do a principal component analysis. So we obtain an experimental spectra, and we can do a linear fit with the standard spectra we have. And then we can end up with the amount of manganese 2, manganese 3, and manganese 4 in the sample we have. And in reality, we usually encounter some other issues, like this is just a screenshot of our data collecting software. We can see the total electron yield channel looks good, but the total fluorescence signal sucks. This is because we also have oxide, and the signal from the oxygen emission will distort our fluorescence signal, which if we use the traditional TFY method, we got nothing. So what we can do, we can get help from our RIXS. So we can take the 2D map of the RIXS for the manganese. And on the 2D map here, we see the manganese L3H RIXS, and this band is the manganese core transition. And this part is actually the oxygen emission. And notice we are sitting at 640 EV, which is about 100 EV above the oxygen edge. So in theory, the oxygen tail is supposed to be flat and contains no features. But in this case, if you have a strong manganese absorption, the penetration depth of your X-ray is going to decrease dramatically, which will end up with less oxygen emission. So this dip really is highly correlated with the manganese absorption. So if we take the integration of this, just the oxygen emission, and we take an inverse of that, we will have a non-distorted manganese LH. And this technique we call the inverse partial fluorescence yield, the iPFY. And then with this manganese LH, we can fit it with the standard spectrum, and then we can end up with the amount of each composition in the samples. So this is our normal working protocol. So for the samples we have, we can measure the total electron yield from our TEY channel for each sample we have. So we can have the LH for the surface. And depends on what element we have, we can either measure the total fluorescence yield directly, or we can measure the transition metal LH and use the iPFY to obtain the non-distorted LH for the bulk. And then we can do this principal component analysis for each sample. So we know at each stage of charge, we have what type of manganese, how much manganese 2, manganese 3, and manganese 4 in each sample, both at the surface and in the bulk. And eventually we can add up these valence, and we can know the average valence of each stage, both in the bulk and in the surface. So here in this curve, we can see the bulk and the surface mainly follows the similar trend. So it's higher valence when it's charged and lower valence when it's discharged. And the surface is generally more reduced than the surface. So this is, you may think this is obvious, but it's actually not always the case. So in this study, we show that when you charge your cathode beyond 4.1 eV, you actually see more reduced species like a nickel 2 or a cobalt 2. This is kind of counterintuitive because you think when you charge something, it's supposed to get more oxidized. So the reason to have this is because when you overcharge your sample, your oxygen anions will become the oxygen gas and it will leave your system. And imagine if you lose your anions, your transition metal will actually becoming more reduced. And this is actually observed more often than this case we had before in all the layered compounds. So that's why layered compound has this problems with the oxygen release and cation migration and disorder, which leads to the irreversibility of the samples. So that's another advantage of the disordered rock salt. So as I mentioned, the rock salt structure tends to be more rigid. So and this will lead to less side reactions. We also have the mass spec experiment to prove that there's indeed less oxygen release in the rock salt materials. So that's why we are trying to develop a new set of a new family of cathode materials known as the disordered rock salt, DRX. Okay, so another example, as I mentioned, the the soft X-ray techniques are more sensitive to electronic structures. So when I say electronic structures, it's not necessarily oxidation state. It also can tell us something about the spin state. So this is another example. We use the Prussian blue as a cathode material. So for those who don't know what Prussian blues are, you can just think this as a solid network of ferrocyanide. So there are two types of iron environment. So the iron that's been coordinated with carbon atoms of the cyanide, and the iron coordinated with the nitrogen atoms. So the carbon end is believed to be a strong ligand. So the carbon side favors the low spin, what we call the low spin iron side. And the nitrogen side is a weak ligand, so it's a high spin iron side. So when we charge and discharge the systems, we can have 4 species. We can have the ferrous and the ferric, and we can have the high spin and the low spin. And the interesting part is when we cycle this Prussian blue, so when we charge it, we have actually 2 stages that are well separated. So we have the first stage and the second stage when it's fully charged, and then we also have 2 stages that's discharged, and it's very reproducible in the second cycle. And if we do the similar analysis on the iron RH, we can see that at the beginning, both iron sides will stay as the iron 2+. And when you start to charge it, it's the high spin side that's getting oxidized first. When you end up with 50% high spin iron 3 and you have 50% low spin iron 2. And when you further charge it, both sides is going to be charged into iron 3. And when you discharge it, it's the low spin iron side that's going to be discharged first, and then both get reduced, and you can cycle this over. So I really like this example, and I feel it should go to textbooks because it's a great evidence for the Hunt rule, where the low spin iron side favors the iron 2+, then you can have all the 3 T2G orbitals fully occupied. And for the high spin, it favors the oxidized form, then you can have the 5D orbitals halfly occupied. So this is really cool to me. And okay, I mentioned that the LH can do a lot of things, but there are some cases that the LH doesn't work. So titanium is an example. So when you measure the titanium 3+ and the titanium 4+ of the LH, you can see they are quite similar. Actually, I even don't remember which one is which, the red and the blue, but I know they are very similar. So even though most of the time titanium is redox inert, but a lot of times material scientists still want to know if titanium is redox active in their materials. It's a very common transition metal that they add into the cathode materials. So we can see that from the data collected by my collaborators. I have to say, sorry, these are very useless because you really can't tell the difference here. But the good part is for titanium 4, you have a D0 configuration. And any reduced form of the titanium, you will have electrons in the d orbital. And if we set at a particular excitation energy and we measure the resonance emission, for any non-titanium 4 species, we have the Stigy band, which comes from the DD transition. So this is like bread and butter. So once you see this DD band, you know it's not titanium 4, and if not, you are sure it is titanium 4+. And in this example, in the 2 sets for materials I measured, I see both remains titanium 4 through the whole cycles in both sets. Oh, I also need to mention that for this kind of emission measurement, you can open up the slits, and each emission will take only 1 minute or so. So the total experiment, so total is like a 10 or 15 minutes measurement. So you probably spend more time like moving your sample around than the real measurement. So it's actually even faster than the traditional X-ray absorption you have. So just keep your mind active. So with the RIXS or the capability, you really have a lot of things to do. Okay. Another example I want to share is the vanadium LH in this lithium titanium vanadium oxide materials. So the vanadium edge is very close to the oxygen edge, so we usually measure them together. And I'm focusing on the vanadium edge now. So the black curve is the reduced form, the blue is the intermediate, and the red and the purple are the oxidized form. And what bothers me when I first analyze this data is I see a low energy feature coming up when we charge the vanadium samples. So does that mean that we have a problem? So I then did a quick DFT calculation. It's really a cheap one. I just do the vanadium and test the different ligand field with different chlorides. And I tested vanadium 3, vanadium 4, and vanadium 5 with different coordination environment. And as we see, when we go from a perfect octahedral to a 5-coordinate or to a tetrahedral, even without a redox, the LH will tend to shift to a lower energy. So this means we have to consider both the redox reaction and the geometry. So here is a great example to show that the soft X-ray technique can also tell you something about the geometry, even though it's like an indirect probe. And we talked to our collaborators, so they went back to measure the hard X-ray, and we can see a dramatic change of the pre-edge here when you charge, and then it comes back when you discharge, suggests the vanadium really migrates upon cycles. And what's more, we can learn is this is the TFY and this is the TEY indicates the surface. And we can see the migration of vanadium actually is more significant on the surface. So yeah, I have shared a few examples of the cation studies, and I will enter my second break for any questions if you have.
Okay, thanks. Yeah, if anyone has questions, please type them in. Actually, I have a question about this last part with the vanadium and to some extent the titanium. Are you saying that the vanadium was migrating, or was it just oxidizing in place? And can you tell the difference?
The vanadium is migrating based on the hard X-ray data. You can see the change of pre-etch here. So here means a high symmetry around the octahedral, and when the pre-etch intensity increases, it's like distorted, at least from. I
guess I would interpret that as a change in coordination or a change in oxidation state, but not necessarily movement of the atom. So is it yeah? Or what do you mean is migrating?
Yeah,
meaning like moving to the other side?
Literature supports this. Okay. Let me come to here. There are also some proposed ideas. So yeah, in this study by Yabuchi, they also propose the vanadium tends to migrate into vanadium 5. So we haven't measured the XAS, so we really don't know. But this offers open question, or at least we are pretty sure there's a coordination number change.
Right.
It doesn't have to be a octahedral to tetrahedral site.
Oh no, sure. I agree that like those suggest strongly that there's a coordination change, but to me, migration means that the atoms were moving from cathode to anode. Do you mean that it's just changing?
Sorry, yeah. When I say migration, it's just migrating
change
among the neighboring ions. Yes.
Gotcha. Okay.
So these transition metal ions are too big to pass through the SEI. So only the lithium can migrate between the positive and the negative.
Okay, thanks. And actually, so you're showing here some K-edge work too. And my recollection is that the titanium is fairly robust or the differences between titanium 3 and 4 plus are pretty robust in the K-edge. Have your collaborators done that as well? I mean,
I don't think they did it because they basically send us. Yeah, a good advantage at our beamline is we can probe multiple elements. So they only need to prepare the sample once. We only need to load it once, and it's pretty fast to switch from edges to edges.
Sure. Yeah. Right. Okay. Great. I don't see any more questions. Actually, but I'm going to make. I'm going to make Jerry's announcements now. So there's time for more questions at the end, but Jerry also wanted me to make sure that everyone would think about proposing themselves or maybe their collaborators or someone as speakers for upcoming seminars, especially in the next few weeks. So if you have someone in mind, maybe yourself, who would like to give a talk in this series, feel free to contact Jerry and volunteer yourself or your postdoc. So with that, let's go on to the third half of your talk. Thanks.
Yeah. Okay. So we now switch gears from cation redox to anion redox. So as I mentioned, the oxygen redox is now a very hot topic in the field. But unfortunately, in the field of batteries, when people are talking about monitoring oxygen redox, they always think of the oxygen K-edge X-ray absorption. So I think this is the right group of people to complain, because we all know the oxygen K-edge is really a transition from the oxygen 1s to the transition metal 3b that mix with the oxygen 2p. So the pre-etch here really reflects the property of the transition metal instead of the oxygen redox itself. So we actually have two examples here from both ends. So in this example, it's a lithium iron phosphate. So we know when we cycle this material, we're actually cycling the iron from iron 2 to between iron 2 to iron 3, and there's no oxygen redox because oxygen is with the phosphate. But here we see a dramatic change. of the oxygen redox, oxygen pre-etch, which suggests the oxygen pre-etch doesn't only correlated with iron redox, not the oxygen redox. In this example is a lithium molybdenum oxide fluoride case. So this is a material designed by our collaborators. So it starts from molybdenum 6. So it really has no place to further oxidize. So the whole cycle of this material is purely on oxygen redox. But here we see, even though this material is a purely oxygen redox, there's little change on the oxygen pre-etch. This minor change comes from the molybdenum migration, again, the distortion of the molybdenum site. So from the forward and the backward examples, we show that the oxygen traditional oxygen KH XAS is not a good indicator for oxygen redox. So in order to resolve this problem, we have to refer to the RIXS. So let's look at the oxygen KH of the lithium molybdenum oxide. So we have, traditionally, we only have 3 peaks. I mark them as 1, 2, and 3. And peak 1 and 2 can be assigned as the EG and T2G splitting, which is pretty consistent with the DFT I did. And if we apply the RIXS on that, we end up with a 2D map, and suddenly we see a lot of things coming out on the 2D map. So we see something sits here, which is assigned as a carbonate, and we see something sits here, which we assign as oxidized oxygen. And notice that if we do integrations along, if we do a total integration, these signals will be overwhelmed by the hybridized peaks. But on the 2D map, they are well distinguished. And for the carbonate, it usually comes out at 534 EV. So let's come back to our LVTO example here. So the carbonate usually comes out at low valence, and it's more pronouncing at the surface, which has to do with the reactions between your electrode surface and your electrolyte, which is mainly organic molecule based. And what's more importantly, it's this feature is what we call the oxidized oxygen feature. So in this cathode material where we have purely oxygen redox, and we can see every time when we charge our samples more and more, this feature is becoming more and more pronouncing. And once we discharge it, it vanishes. And we can, to better analyze that, we can take a RIXS cut right at this 530 EV, and this is what we have. And this shoulder corresponds to the oxidized oxygen feature. We see when we charge it, this peak gets more and more intense. And when we discharge, we lost this feature. And when we charge it in the second cycle, it shows up again. And it has a very nice correlation with the capacity here. Even though it's not like a perfect linear correlation, but it's highly correlated. And what's even better is we have measured tons of samples. So no matter what type of cations we have, as long as we have oxidized oxygen, we will have this oxidized oxygen feature. Doesn't matter if you have manganese or a nickel or a high entropy material. So we really call this the fingerprint of the oxidized oxygen. And it's now the slam dunk technique in the field of batteries to measure, to see if there are any oxidized oxygen cycled in your electrode. So with that, we can combine the multiple techniques. In this lithium, nickel, molybdenum, titanium oxide, and fluoride material, we can combine the nickel LH, the molybdenum LH, and this oxygen RIXS. And of course, we also measure the titanium emission to show that there's no titanium redox. And we can couple this with the electrochemical profile. And we know when you charge it at a low voltage, it's mainly the nickel redox. And at high voltage, so the nickel voltage stops, or the nickel redox saturates, and then it's the oxygen redox that's kicking in. And when you discharge it, the oxygen redox and the nickel redox kind of like mix together, and at a low voltage, you can see a tiny molybdenum redox. So with this technique, we can really isolate the contribution of different components in a like high entropy or whatever cathode materials we have. So this is a really powerful technique for those battery scientists. Okay, so that's so much of oxygen redox. Since I still have a few minutes, I'm going to talk something about other anion redox. One, not necessarily redox. So one is the fluoride. As I mentioned, so we have that magic fluoride effect in these materials. So the first thing we want to know is the bonding of the fluoride in these materials. So this is just the standard fluoride XAS. So we measure in these battery material, we measure the transition metal fluoride, like a lithium, niobium fluoride and a manganese fluoride, to see what a transition metal fluoride covalent bond look like. And we also measure the lithium fluoride, indicate an ionic bond. And when we measure our real electrode, we see that it's mainly ionic interactions, means the fluoride really moves, has a weak interaction with the transition metal ions. And what's more interesting, we can see when we cycles, in the first cycle, we lose a lot of fluoride intensity. And in the 20th cycle, we almost lose all the fluoride in signal, which suggests these fluorides were either dissolved into the electrolyte or is going to be covered by something on top. So we can observe that using our PEY probe. Okay, another example of anion is sulfide. So our collaborator tried to replace the oxide with a sulfide. So this is a iron sulfur based cathode. So we have shown that there's some, obviously there should be some iron redox, but we don't know if there's any sulfide or sulfur redox. And if we measure the traditional sulfur absorption for the pre-skin powder, it looks okay. But when you make it a electrode, you have to mix in a lot of carbons. And at our beamline, when you have a lot of carbon mix, the signal is going to be dominated by the second order carbon, and you really can't see any sulfur signal. But if you look at the RIXS map, even here, we can see we have the carbon emission here and the sulfur emission here. And we can really just focus on the sulfur emission doing a partial fluorescence yield. And we can see when we charge and discharge the electrode, we have the sulfur being oxidized and reduced. So this really shows the power of RIXS. And so we can really obtain or really probe some weak signal that cannot be done by the traditional absorption method. And with all that, I'm going to sum up my talk. So I showed at our beamline, so we use a series of techniques, soft X-ray based, to understand the redox behavior in different battery materials. And in the title, when I say multi-channel, I really mean the multiple elements. So it can be both cations and anions, and we can probe the surface and bulk, and we can measure the traditional XAS, XES, and there are tons of information in the 2D RIXS map. We can study along the excitation energy, we can do integration along the emission energy, and we can really focus on the certain part of the 2D RIXS map. So there are really a lot of things we can do. And yeah, we are open to any potential collaborations if you guys are interested. So yeah, I guess that's, oh, I have to do the acknowledgement. So I want to thank my PI, Dr. Wan-Bi Yang, for his support and help to teach me. So I came from a biochemical background with synchrotrons, and he helped me to have a smooth switch to the battery field. And of course, my colleagues at ARS to help maintain the system running. And I'd love to thank all my collaborators who provide me this fancy materials so I have something to play with. And I'm supported by a DOE BRX project. And now I can take your questions and comments you have.
Okay, thanks. That was great, Yang. That was really great. So Yulia has a question, or maybe two or three. Go ahead when you're ready.
Yes, thank you. Very nice presentation. Thank you very much. My question is for one of your RIXS maps. So on most of your RIXS maps for oxygen, there was just like one lowest peak, and then there was a peak on the side. But there was one material which had like double peak, and it looks like they were double shifted. So I was just thinking, yeah, like the one in the middle top.
I'm not sure which one you're talking about, but the oxidized oxygen feature is really conserved. It usually comes in at the 531 excitation energy and 524 EV emission energy. So that's the good part of that. So no matter what samples you have, the oxidized oxygen energy is very conserved. And other peaks has to do with the hybridization of your transition metal with your oxide. So this is, I think I did a DFT calculation here. So these two peaks corresponds to the EG and the T2G set. And notice when you have more than one type of transition metals, when you have nickel and the titanium and the molybdenum, all these hybridization features, they tend to mix. So you will end up with something ugly. So
yeah, so my question was,
the oxidized oxygen can be well.
Yes, I understand.
Okay.
So my question was only for the particular single image, which is lithium, manganese, niobium, oxygen, fluorine, the one which is in the middle here, middle top. Yes, this one.
Okay.
My question was, you see like both peaks, they can kind of have a feature on whatever low energy side, and one you attribute to oxygen, but I'm wondering about the second one. Is it just like, for example, if you have discharge material, is it also like, this guy, yeah.
Okay, this is actually just the expansion. So because this peak is more intense, so it has like a broader width, depends on your color scale. So this one is more intense, so it's broader, so it's expanded to all directions. I guess in the traditional XAS, we only consider the peak width along the excitation energy, but in reality, it actually comes into 2 dimensions.
Okay, and my second question is, do you know what is the chemical nature of this oxidized oxygen?
That's actually a very interesting question. So my answer is we don't know at this moment. But since it's a very hot topic, there have been lots of debates on what type of the oxygen we have. So the Peter Bruce group from Diamond, they assigned this as a triplet oxygen gas that's being trapped inside the lattice from their like a RIXS measurement. But we not necessarily believe that because it's not consistent with the Raman peak, the Raman vibrational frequency we have. So I guess it may be something corresponds to the photo damage or something. But yes, so we are still working on that.
So I'm sorry, I will have to clarify. So do you think this feature is photo damage, or what is photo damage? I didn't get that part.
Oh, this feature is not for the damage, because we always do a photo damage test every time we start our experiment. So this feature is a oxidized oxygen. So what I can tell is it's similar but looks different than the pure oxygen gas we had measured. So if you ask me, I personally believe it's a peroxide species based on my own DFT calculations, but we still need more evidence to lock that in.
Okay, thank you very much. And is this published data? So can I see this publication?
Some of the papers are published, some of them are still not published. So I will, so you actually in the announcement, you will find a list of related publications you have. And if you need more, or if you want to discuss more about this like technique, we can set up a like a private conversation. That's fine.
Okay, so Tim Hyde also has a question. Tim?
Hi, Hank. Thanks. Very interesting talk. My particular question is related to the oxygen non-redox pre-edge feature that you showed in lithium iron phosphate.
Yes.
Again, is that published work? And could you just please again go over the origin of that feature?
Okay, so this is a published results. It was found, it was published, and it's actually been reviewed again in one of our in a review done by my PI, and I think you can find that in the first reference we had in the announcement.
Okay.
And my understanding of this is this peak only corresponds to the iron 3, because iron 3 has a higher Z effective nuclear charge. So this feature is well separated from the rising edge. When iron is reduced to iron 2, it's going to migrate it to higher energy. And actually, if you see a shoulder here, which may correspond to the feature of the iron 2. So, and for more details of explaining such pre-edge thing, we also have this review. It's a very comprehensive review on ligand-based XAS.
Sure. Okay, thank you very much.